So hi everyone, and yeah, in today's class we will be discussing about some of the most important topics that we have left out in the last classes. Okay, and yeah, and we will just try to cover the important things. And in the last class, some of the parts it's not been recorded. Okay, and I'm going to upload it right now. Okay, and the other things are I have uploaded the assignments in the um, drive. I have shared the link in the portal also. Okay, and hope you will be able to access it. And yeah, let's start the session then. Right. So in the last lecture, what we have saw is we try to analyze the population dynamics in a two-level laser systems. We know that you need to give a large amount of energy for the things to excite up in terms of a three-level systems, and we are going to study it in a detailed manner in today's class. Okay. So in the hope of seeing if we can able to generate optically pumped two-level system or not. Okay. So the population that can be distributed equally between the level 1 and the level 2 and not anymore. Okay, so if you're talking about the two level systems, okay, so often it is a lesser. Okay, and if you do not generate, then it is not possible to have a laser systems. And this process of having more number of molecules in the excited state than in the lower state for our emission, we call them as a population inversion. So ultimately we need to understand about the population inversion, that is high number of molecules in the excited state when compared to the lower motion of the state. And then we are into the two level system, and we know that it's not going to be this possible. Okay, so right now we are going to deal with the three level systems, what exactly it is. Okay, so it is possible to achieve a population inversion over here, but how much amount of energy that we are going to spend on it? So that makes a big deal in it. So we are going to deal with that in today's class. Okay. So let me just give a glimpse about the parts that's been covered in the last class then. Okay. So today, okay. So first we will draw about the systematic diagram. Okay, give me some time. This is K absorption. Okay. This is first, second, and third level energy state. Okay. So non-radiative. Okay. So this is a three-level systems. Okay. Thank you. The same goes for the second part also. Ultimately, we have to achieve the conclusion, that is n2 minus n1, to achieve the higher population inversion. So, so let's have a quick thing about what we are exactly discussing. So in a two-level laser system, what's exactly happening, it is that the light radiation that we are actually using to pump up, it's exactly the same that of the light radiation that is actually introducing the stimulated emission. So you need to rise the molecule from one energy level to the higher energy level. As a result, it is constantly competing the molecule, okay, taking them to the higher energy level, okay, from up to down and down to up, okay. That is the movement of a molecule, okay. So the higher population in the level 2 being, it is not visible. So you go like the two level system get failed mainly because it couldn't able to achieve a higher number of a molecule at the higher energy states, okay. So what we are doing is that we are actually stimulating, okay. The absorption is a K absorption is a dependent on the incident light radiation. So is a KST, okay. So K absorption and KST, that is a stimulated emission, all depends upon the intensity, amount of incident light that's been struck on the surface of a ground state molecule. So this is also depend upon the pump laser, right? So the laser that is taking, or the light that is actually taking the molecule from the ground state to the higher energy state. So that pump light, so as to speak. So we will call them as a KP, okay. K, but the superscript is a PAB, okay. So they try to just achieve the population inversions on the basis of amount of intensities, and those absorption as well as the stimulated emission depends upon the both, okay. So light is which is incident on the medium can actually take the molecule to the excited state. So we know that when the light is hit on the surface of a molecule, they will automatically go to the upper energy level. But the lasing per se, right, that also requires, or remembers, that also requires the stimulated emissions. It has to come down, okay. That is also the whole idea of a lasing. So in order to achieve the population inversions, how fast we can able to achieve a certain sort of a thing. So but the lasing takes place between the two level, either it can be the one, okay. And uh, and how we are going to achieve those kind of systems. So there are spontaneous emissions, okay. So we can actually think of them, okay. And yeah, So spontaneous emissions, we will be just talking about them when they will be coming down from the higher energy level to the lower energy level or ground state also. Okay, so there are two kinds of emissions we have to focus on. One is a spontaneous, another one is a stimulated emissions. So we want to differentiate these two things also. Okay, how? Okay, so how they are actually just making the transition from one energy level to the another energy level. Okay, spontaneous emission is happening from a third to the second. So here you can see that, right? So the third to the second, so spontaneous emission. Okay, so yeah, state 1, and this spontaneous emission is happening from the state to the 1 also. So this is also okay. One is a non-radiative one and another one is a 2 to 1. Okay, so when we see this when we see this, we are finding out different numbers. So numbers are nothing but 3 to 1 2 and 3 1. It's nothing but the things are coming from 3 1, 3 2 is 3 to 2, 2 to 1. Okay, so this wiggly arrow represents the non-radiative decay from our level 3 to level 2. Okay, and non-radiative, and it is happening it is from level 3 to 2 only. Okay, so there are direct applications or direct use of the Jablonski diagrams you can think of, because we are actually representing only the electronic energy level. So when we get into the 4 level lasers, we actually will be talking about the electronic states of your matters, and then we will try to arrange all of them in a single curve. Okay, so the rules following that we are actually sticking to it, so we can see how useful it is actually to draw the potential energy diagrams of all of these things. So yeah, so at the end we have to see the transitions. Okay, and we are using this the transition n as a total of n1 n2 and n3 also. So and the rate of transition that's been can be easily described as d1 divided by dt, and this is the whole of it, what exactly happening in each of the phenomenons, and the same it goes for the dn2 divided by. Ultimately, whether we will be able to achieve the population inversion errors or not, this is the one, whether we were able to just achieve this thing or not. Okay, so yeah, so we can write Kp, the stimulated N3 plus this one. Okay, stimulated Kp N3 plus stimulated 2 1 N2 plus Ksp is 3 1 N3. So the same goes for the Dn2 divided by D1, and ultimately we want to achieve the population inversion, and we are going to get it to the conclusion how we are going to separate the N2 minus N1. So these two phenomena have a role to the play upon. Okay. So how we are going to name all of these things in terms of a rate of transitions. So finally we just need to achieve the population inversions at the higher energy level, and this can be achieved by denoting or subtracting the two of the most important rate of transitions. So n2 minus n1 divided by the total. Okay, the change divided by the total, and we will be trying to figure out what's exactly happening, whether we will be able to achieve the population inversion at the 3 level laser system or not. Okay, so that's the most important part. Okay, and we can also go ahead and verify this by ourselves to deal to make it as a good deal with the answer. Okay, so to get an idea about how much the percentage of a population inversion can be researched, we know that the two level system is not possible because you need to make the higher amount of energy or molecule on the higher energy level. Okay, but that's not it is happening. Okay, but in the three level systems we can able to do it, but it depends upon the amount of intensities, okay, the percentage of intensities of a light, okay. So yeah, here we are representing this is the gamma, and we will soon learning this about what exactly the gamma function it is, okay. So and absorption is received by k absorption divided by k is spontaneous, minus 1 divided by 1 plus 2 gamma k absorption by spontaneous plus 1 also. So gamma here is kind in the case of a spontaneous, okay. So now the gamma is essentially the ratio between the spontaneous between the level 2 and 1 by k n or between the level 3 and the 2. So here we are representing this is the what is exactly the gamma, or how we are denoting the gamma terms. The gamma terms is been presented as the ratio that is of a spontaneous between the non-radiative pathway, okay. So yeah, and the ultimately it has to remain either positive. We need to just make sure that the number k absorption by k spontaneous need to be greater than 1. So this is gamma. The gamma has to be remaining greater than 1 in order to make sure that every term remains positive. If the negative is occurring, then the population inversion is not achieved. That does means that only the small amount of molecule are in the higher energy level, okay. So that is no problem, because absorption here we are talking about the pumping rate, how much you can able to pump inside it, and then this is the spontaneous emission rate also. This also depends on the spontaneous emission rate. Pump to make sure that everything in the higher energy level, and the spontaneous emission rate in order to make sure that everything comes to the ground energy level, and then the wiggling arrow shows the spontaneous emissions also, okay, emission rate. So we can actually increase the incident light intensity and make it to the 1, that has to be greater than or equal to the 1. However, the important thing here is that we need to make sure that gamma is not less than 1 also, okay. So okay, so the whole process are going to generate a delta n being a positive. That's the only thing, so that we are achieving the population inversion. So that's the one ultimate aim, okay. How we are going to do it? So we know that gamma is the ratio of a spontaneous emissions, okay, between the energy levels or lasing levels. Lasing level is nothing but the system that achieves the population inversion, 2 and 1, divided by the inflow rate. The rate is a constant k, the non-radiative is rate constant. So again we are mentioning about the gamma only, what exactly the gamma function is all about. So we can able to see such that they can't be less than 1, okay, needs to be greater than that, okay. So yeah, so we can also, we have been discussing about the graph. So whether at what state of a condition your laser action or lasing this will be the phenomenon, we know about that. We can discuss about the thing in terms of graphical intensities also, okay. So this is 0 minus 1 plus 1, it will go just like this. So this is the region where the lasing phenomenon occurs, so to achieve the population inversion. And this is not the one. So the x-axis is intensity. I hope I'm not wrong. Okay, incident light intensity. Okay. So yeah. So ultimately, we need to reach the condition I told about this important point. Okay. So KNR, that is 32 should be greater than KSP Q1, and K absorption is directly proportional to the amount of incident light, okay. Okay, so this can also make sure that whether the gamma has to be less than or greater than 1 in order to achieve the lasing erasure phenomenon, okay. So but the bottom line, what exactly we are discussing is all about, okay. So we can actually, by changing the or choosing the particular the media is nothing but where the laser can either penetrate or pass it in a specific way. We can actually make sure that the delta n is greater than 1, it remains positive also. Okay, k absorption by the k spontaneous, where the k absorption need to be larger than the k spontaneous in order to make sure that they are completely greater than 1, so to have a good population inversion, we will try to populate the more number of molecule into than in one. So this is the basic phenomenon how we are going to populate the higher energy levels. Okay, so the interesting phenomenon that one can actually plot this inversion, right, or to say that the ratio that is delta n by n or delta n itself is a function of the incident light radiation. I told about that. Everything depends upon the intensity of an incident radiation. If it's high, definitely the things will happen. If it's not, then the population inversion won't achieve. So that's why we plotted that graph at what place the lasing phenomenon will be occurring. So as we keep on increasing the intensity of your incident light at one point, it might crosses the 0 and then approaches closely 1. So we know about the limit, right? So in terms of a calculus, if you talk about the limits, so the limit x tends to a or b only they will represent. Okay, the limit will tends to grow till the particular point, but it won't even reaches over there. Okay, x tends to a means it's going to the a but haven't reached the a. Okay, that's how we are naming this also. It will never be able to reach it because it is only a small, it is only the non-radiative pathway. Okay, and the spontaneous as well as stimulated, we will see that molecules has a three pathway to follow. So in a three receptor pathway, you need to give a large amount of energy for the molecule to exceed, to jump from one state to another state. Okay, and we will be talking about that. Okay, this is the state level how we can able to understand in a more descriptive way. So what it means. Okay, so we have to really increase the intensity pretty high. Okay, so to get any considerable number of molecule in the higher energy level, but then at the point in time, whatever the molecule that are present here needs to be lesser than the particular thing. So we have to know two things. So this is the one most important part. So here what you have seen is the most important. Now another one thing it is, so we have to number of molecule. So this gives the detailed set or perspective to gamma function, whether it has to greater than or less than or equal to 1. So yeah, so in order to achieve the population inversion, okay, this is one of the most important part. Yeah, so and then the efficiency. So finally we have to consider one of the most important thing, that is the efficiency. What exactly the efficiency is all dealing with it. Okay, So defined as the amount of light intensity that you are actually pumping it into the amount of the emitted light intensity that you can get out. So whether it is matching out input to the output, or the input is quite higher than the output, or output is higher than the input or not. Okay, is there any loss is happening or not? Ultimately it should have to be a gain, but it should not be in the loss. Okay, so and there are lasers practical. So there are lasers with a 3 level system that can be approximated to the 3 level system also, and we will see much more about the 3 level system in the upcoming lectures. So the first laser is one of a kind, that is a ruby laser. We have seen in the last class also. Okay, it's a 3 level system only, and it's not been quite high use because it needs a lot amount of an energy of incident light. Okay, and in order to convert into the laser itself. On the other hand, okay, how is there any way to improve this 3 level system or not? Okay, so there are many ways to improve the 3 level system, mainly because it serves as a drawback that you need a large amount of an energy for the things to get increased from one state to the another. So the idea is pretty simple and it's straight to the forward. The reason why you are having the trouble is because you are fighting against a number of molecules in the ground state. So the problem is the number of molecules that are present in the ground state. So you have to create a extra resist state, high level state. You can actually start accumulating so that your incident light does not compete with the laser light also. So you can have an extra light, so extra state, extra extra stage you can say. So this is accomplished with this stimulated emissions only. So we can actually start accumulating the number of the molecule in the excited state. However, what is happening is that you are actually, the laser emission is mainly measured by the difference between the number of molecule in the excited state and the ground state and the lower energy state. Okay, so between which the lasing is happening. So here is the, this is the most common phenomenon. So whether the laser emission is measured by difference in stages between the number of molecule in the excited state, ground state, as well as the lower energy state, whether the laser is happening or not. Okay, if so, what exactly the amount of the power? Okay, so you are always having a large number of molecules in the ground energy level because it is being supplied by the stimulated emission, spontaneous emissions, and then the spontaneous emission from here as well as the stimulated emissions. So all of this phenomenon are a role to the play upon. Okay, so the natural emission, okay, would be, this is suppose if we had a laser systems, the lasing occurs between the level that is not inclusive of the original ground state. So we will get back to this line what exactly is all about. Right now we will think about the 2 level system, and we have overcome the problem in the 2 level system with the 3 level system. But the problem with the 3 level system is it needs a much more amount of an energy for the molecule in the ground state to go from one state to the higher energy level. So how we are going to overcome that? Okay, so if that were to be the case, then we can actually see practically how we are going to maintain the level of the population at a one particular stage. Okay, so yeah, so there are, and so the we understand the problem. We have a 2 level system, 3 level systems, and we faced a problem with the 3 level system also. 3 level system major problem is it couldn't able to just achieve the part because it's using a too much of an energy. So but there are many lasers, and we have also discussed about the thing that can be just overcome by having an extra one stage, that is a 4 level system. Okay, can be approximated, and we will see all those laser as an example in these courses, and how we are going to generate a lasers. Okay, and special attention to the nature of the electronic states of this material also, and we will be seeing about the gas discharge tubes, other things that is capable of generating the laser phenomenon, I mean, how and what kind of analysis or what kind of the properties are exactly looking at. Okay, and so yeah, so the kind of serves as a quality check whether it can or cannot act as a lasing medium for the population inversion to occur, as well as for a thing to be optically pumped in the later cases. So we can able to generate much more quite high phenomenon also, and we are going to use a light to generate a light of a particular a kind, that is a laser, and that we need to pass this as quality check. Okay, so and we will talk about an important category of lasers, the lasers, that the categorization of laser in terms of the light intensity as a function of a time and the behavior as a function of a time. Ultimately the coherence and the spatio-temporal everything will be taken into the considerations. What is exactly the spectral properties? Why is it useful in our experimental condition to achieve a maximum population inversion? So yeah, so in the next lecture, the coming research part, what we're going to discuss is, just give me a minute. So yeah, so the next part that we're going to discuss is how we are going to construct the four level systems. So let me draw this four level system. Okay. So yeah. So now we are going to talk about the four level lasing systems, and we will get into the things. Okay. So the precondition for our being able to set a new net emissions of a light through stimulated, okay, through stimulated emission, net light coming out from the devices also, and we ultimately we need to research a population inversion. So we looked at the different possibilities of the electronic state configuration in the lasing media where the light can be passed across this, and we will get to achieve this better things. Okay, and each of them requires a different and many stuffs and different condition for the existence of the population in motions, and then towards the end we were actually looking this at the flow level systems also. Okay, So in the previous case we have discussed about the n2 minus n1, n3 minus n2. Here we will be talking about the n3 minus n2 to achieve the A system. So this is the most important part in it. Okay, this is the this is the important point that we are going to discuss. Okay, and so we normally used to call this as a 4 level systems, and how we are going to increase the order of energy and the process we indicate through the arrows also. Here we have indicated everything in an arrows, and so the population fraction of the population existing as a higher populations, where the delta n here is actually the delta n real number of molecules in n3 minus the number of molecules in the state 2. So n3 is a minus n2, that's what we are trying to do it. Okay, so the lasing is normally happening between the levels 4 and 3 only, non-radiative the path, and the stimulated emissions we are trying to hone in on, and this is the stimulated only. Okay, okay, so we can call that as a stimulated emissions, and we can call that as a lasing also. So here, so 3 to 2, 4 to 3. Okay, so this is the whole idea here. So in this process we can actually see or write down the expression for delta n by n. So what exactly the thing is, just like in the last 2 level systems, here also we are going to write an expression for delta n by n. So yeah, let me write it down. So delta n by n is equal to, we know that knr 21 minus ksp 32, and we know that amount of the incidence light also plays a major role, and then absorption 23 k21 plus k43 plus ksp32 k21 plus k21 k43. So this is a non-radiative, I told about that. Okay, and so finally, as again n3 minus n2, we need to achieve the population inversion, and that is a lasing condition 3 and 2. It should be this greater than 0. Okay, normally in terms of a 1. So how we are going to achieve it? So the rate constant, that is a 2 1. Okay, it's normally divided k21 by nr. Okay, so we are actually representing them as a non-radiative pathway 2 2 2 1. Okay, so this is a leap rate at which the ground lasing level is being depleted to the ground level of the molecule itself. So now so that we can able to write down a clear cut equation, this is that dou n by change in this rate of transition, that is n divided by n, to achieve the population inversion in a particular level also. Okay, okay, and essentially we try to mean a lot in terms of the rate. The rate is larger than the spontaneous decay rate. Okay, so and that's why we used to call it as a case spontaneous also. And as long as the rate is faster, you always see a residual amount here and there, which means it will be the best be something that has a value greater than 0. So the depletion rate is larger than the supply rate, and so it is, this is the rate determining steps. So you have to focus on the rate determining step also for the maximum reverse output. At the end of the day, you will be having a maximum number of molecules or no molecule at all. It is never the case where you have more molecules here, unlike it is other our 3 level resonators, where there is more number of molecule than at the ground state. Okay, so because there were two these two states were overlapping it is also, that is one of the major drawbacks. Okay, so now as long as this is ensured in your molecule, you will be always having this delta n be this is 0 or greater than 1. Okay, and yeah, and that's one thing. So that goes directly, and we will see that being it is higher, what we are able to basically keep. Okay, so if you assume, make the assumption that knr is larger than the spontaneous rate, so as long as the number is much greater than the entire as a denominator, that is, we have already spoken about it, right? Okay, um, spontaneous KNR, so the gamma. So in order to achieve there is a population inversion that will take place in the two level systems. The same thing that we are talking about that. So we can just actually try to understand the constant for a given molecule that's been under the ground level, and whether we were able to maximize the number of molecule at the higher level or not, how we are going to outreach it. So that is the crux of the matter. So we can able to see the 4 level laser. That's how they will be making efficient errors or not. So okay. So now we will see this about the conditions. Okay, how whether we were able to replicate in terms of the lacing actions. Okay, you consider the tubings. You can call this as a media. Tube. Okay, highly reflective mirror will be there. Okay, the laser light is striking here and there. Okay, and there were different picking across also. So yeah, so whole length. Ultimately, we try to cover the Beer-Lambert's law. Is equal to 0. Okay, this is M1 and this is M2. Okay, and R is equal to N0 divided by Ni. And I will try to note down the equations, and then we can able to explain what exactly the each of these terms contribute, whether they try to understand about the concentrations of the particle in the solvent or not. Okay, I of C is equal to lambda dot C dot G G Nk del n is equal to Nk minus Ng, that is greater than 0. Ng that is greater than Nk. So note that now that does not guarantee that if you take a material, even if it's a 4 level systems, and we try to also call one thing as a media. Okay, so then we try to place the two conductors or reflective surfaces. Those are the mirror. One end will be the highly reflected, another one is a partially reflected. So we call them as a M1 and M2. Here we place, right. So one will be termed as a M1, another one will be placed as M2. So typically this is the way it is normally done, by having a discharge residue for the lacing system or things to be done. This is like a flash lamp that is wound around this medium. Okay, So what is exactly happening is that light flash that is being generated in the discharge tube is going to energize the media, and then the media is going to fluorescence. The thing that the substance that is present in the media is going to lighten it up. Okay, so the fluorescence, we are tapping this onto it completely defined the fluorescence, and to make this as a round trip here and there, more and more molecules in the excited state, and we are trying to bring down the molecule more and more from the excited state to the ground state also. So here we are talking about the situation where we have created a higher amount of molecules in the both the excited as well as the ground state, but the population inversion, to achieve it we need a number of molecule at the excited state. So these guys, the fluorescence photon, when they come back, they actually are going to bring down the more molecules and generate a more number of photons of their own kind. And the lasing is nothing but the light amplification through stimulated emission of a radiations. That's why people used to have the photon multiplier tube at the end of the reaction mechanisms also. The photons that are created through the stimulated emissions. So let us do a little analysis of what is exactly happening with all of the systems. So the gaining the media, so that is a media that which we are hoping to gain or convert the light energy that is of one kind, right, which is of incoherent light, coherent light and incoherent light. Okay, so what if we try to do that, the light energy that is existing as an incoherent light in terms of the discharge lamp or a flash lamp alone, and that is being used to generate the fluorescence, the intensity. Okay, now we want to make sure that the energy delivered through the first lamp is efficiently or is converted into the energy of a stimulated emissions or not, the photons of a stimulated emissions. Okay, so here what we try to describe is what happens to the photon density when the photon pass through a set up there is something like this. So it goes and this strikes here and there. What exactly is happening? Whether it will be able to reach the population inversions or not. So ultimate aim it is of learning all of the system is to observe about the population inversion only. So the medium is going to interact with the light, and we know from our starting classes itself, when you have a medium of some length, this is the whole length of a system, and we know what to do or to describe the intensity of the light that is traversing across the media. Okay, it's going to and fro. Okay, when the media is going to interact with the light, whether the light is making any changes to the media or not. So this is given by the simple expression that is a Beer-Lambert's law. So we are going to write this on the z axis. So intensity as a function is of the z axis, that is why it's been mentioned as the z. So here the z, it is being mentioned as a thing. Okay, and yeah, so what will be happening, and what is the intensity at the beginning of the medium, to the power that is minus epsilon of lambda. Okay, the frequency. So frequency here we are representing it as a lambda. Okay, okay, and C and Z. So one is absorption, another one is a stimulated emissions. So in a regular absorption, a spectrometer, so we do not have the molecules in the excited state. The regular absorption spectrometer, we don't have the molecule in the excited state. Okay, so we ignore the stimulated emission terms in terms of absorption spectroscopy, not here. So but here we are going to talk about the stimulated emission eventually. Okay, in absorption spectrometer there won't be any number of electrons at the highest state, but here we are going to talk about the stimulation emissions, and mainly to recast the consideration in terms of number densities of the molecule that are present in the ground state and the excited state also. Okay, so if we go ahead and write it, it is actually, so we are going to write this, see this in terms of number density in the ground state minus the number density this in the condenser. So that is n this concentration, this one ng is a minus nk, and that's why we have mentioned it. This is, so at the room temperature we can see or say that Ng is far greater than Nk. So 1Z is progressively less as the light travels through the media. Okay, so something will happens. So the how the light will be this traveling through the media, what exactly happening it is. So in a particular axis. Okay, so intensity of a light at a particular axis goes down, is commonly less than it is 0. So we say that light is being absorbed by the media through the interaction. So if it is less than it is 0, then we can able to make a conclusion that something is happening at the interface of the media. So in our case, the special case of the four level atom, and then our way of generating more number of atoms or more number of molecule at the higher energy state of the emission among the emission levels. So the population is in motion essentially means delta n in our case is nk is a minus ng, that should be greater than 0, and this should be greater than 0, and in order to maintain a proper population conversion. So how we are going to write the whole set of an equation in terms of a Beer-Lambert's law is, we know about the certain things and we will be targeting it as about the selectable ones only. So the intensity or incident light, the frequency Ng minus Nk lambda Nk minus Ng say E minus so this is the length of the media. Okay, what is happening exactly happening at the each reflecting surface? This is, so the gamma function can be returned as a function of 1 minus the reflecting surface epsilon it is of lambda of it as a scattering, sigma of a scattering, and the I is equal to I naught e power minus gamma. Okay, so clearly the intensity will always be a function of the lambda, that is a frequency. So there are different lambda that get absorbed. To be this a complete, we should actually write this lambda comma z, and so this is. So how we are going this to understand what exactly all of these terms as respective about. Okay. So what we see, there is a gain in the intensity at the end of the expression. There is an increase in intensity, and it is precisely because of the of this, right. So you can actually create a population inversion state. The media that you are talking about becomes a gain media, because when you actually normally pass the light through a media, it is going to absorb that, right. Okay, so they are making a point that the intensity is gain, and you can able to achieve the population inversion also, because the light is being absorbed by the media itself. So because of the population in motion, you can actually gain the intensity that is coming out from the other end also, one end to the other end, and you can able to increase the population in the gain, that is nothing but the increase in the number of molecule in either of the states. And finally you can see the intensity at the lambda of z is actually supposed to be z, and it's been corrected also, and how much of the intensity gain will have a function, okay, of the length of the gain in the media. But the key here that we need to just consider few thing is how or which is as the light travels through this setup, okay, will be the entire light that is hitting on the M2 is not reflected back or not. So we have made M1 and M2, one will be the highly reflectance, another one will be the less reflectance, and whether the light that's been transversing across the media, it will be able to make a certain sort of a gain or not. Okay, so it depends upon the reflection coefficient of the mirror also, okay, the scattering, and which is the fraction of the light that is so defined as a number of photons that are reflected by the total number. So that is the reflections of the mirror. Okay, so which is the mean number of a photon that are reflected by the number of photons that are kind of an incident also. Okay, you will see that this number is at the best. Okay, but it is never equal either to 1. So at every such reflection there will be a losses also. We will see the quite high loss in every of the phenomenon. We need to take into account the losses. So the first loss we are going to talk about is mainly due to the reflections. Okay, this is the reflections, and the loss due to the reflection is mainly given by each of the mirror reflecting surface. We will be having a loss of 1 minus r, and we will take a look at the gain. It is a round trip also, and we would like to just imagine a photon that originated from some place, and it moves along the length and reaches and spreads across the things, the whole the media, to and the forth, because of the reflecting in the mirror also. Everybody has gone to the excited state, and some amount of a spontaneous emission that is possible either from one part to the another one, 3 to 1, okay, or 3 to 2. The spontaneous emission is the most common phenomenon that we'll be talking about in order to make sure that the inversion has been taking place. So this is all about the one full round trip that's been happening, and then idea main is the gain of the photon will have when it passes through the media or not. So the probability of loss or the fractional loss of a bunch of a photon we will encounter about that also, and it means the whole system will set to operate in order to generate an output only if you have a gain higher than the loss. So they are already claiming the point that it can able to produce an output only if there is a gain, okay, higher than the loss. So we are going to equate that to tell us to compromise to arrive to the conclusion that threshold at which you will start seeing this is the lasing. Lasing is nothing but the population inversion. So this is kind of a very simple idea, and we have also denoted the losses, the reflectance, scattering losses. Okay, so there are many reflection losses, and this is completely a function of 1 minus r. That's why we have put the gamma, the function of 1 minus r. So the absorption of the emitted light, okay, that will also happen. That is why it's been repeated as epsilon, and the loss of the photon due to the scattering also, okay, and other such limitation, right? So we will call the scattering coefficient at some sigma, okay, to the power, and we can actually combine all of this expression because this is relatable to the gain, and to get the net result output, right? So in order to make sure we are able to follow all of these things, we can rewrite all of the result in such a way that n at 2l minus gamma, okay, and 2l, and this is nothing but the 2l, it's traveling to and forth, and the length. So you can write down the original quantities or variables in such a way. Loss coefficient of guiding. To achieve the population population. So yeah, So what we try to achieve is, so it normally to consider the amount of photons, okay, from one end to the other end, and whether with the help of epsilon or the lambda as well as with the del n we will be able to achieve the population inversion or not. So that's why the del n should be this greater than the lambda, the loss coefficients. So okay, so the 2L is nothing but the round trip that's been happening, and we need to have a higher amount of our gain in order to overcome the losses. That's why we just need to consider all of this phenomena. So here we are actually looking this for a delta n, okay, which is nk minus ng. So if we need to build up the population inversion above this gamma, that is by greater than symbol, we will be saying the lasing to achieve the population inversion, the fraction of the population inversion as a function of a incidence, the amount of incidence light. So we can actually see the lasing will not happen as soon as the things recover over the above, and the delta there is n above this, and only in a particular region we can able to see the lasing there is also. Okay, so we can already this put into a photomultiplier tube or any photo detector and plot this as an output as a function of incident intensity. Okay, we can just have a thing. So we have already talked about this phenomenon, that is a lasing error conditions. This will be looking like this. So intensity, incidence, this is lasing, this is the radiative pathway, okay, non-radiative pathway. So this is the place where the lasing occurs. So we'll kind of slowly increase until the intensity that we want to measure, okay, are completely there's a matching out, okay, and ultimately you will have the lasing, that is a population inversion, and we will talk about all of this the properties in the upcoming lecture series. The next one that we are going to talk about is different types of phenomenons that relatable is to your lasers. Okay, so next one is relatable to the lecture 29. Just give me a minute. So the next thing that we are going to discuss is different types of lasers. Okay, so how we are going to this overcome all it. Okay, so yeah, So we can possibly use and then the conditions and that need to meet in order for to create a lasing resin medium if we have to use them in through optical error pumping for the population inversion to occur. So we went through a 2 level, 3 level and 4 level systems also, and we said that 3 and 4 it is possible to have through the 4 level laser or lasers are based upon the efficiency. So yeah, so we will see some more examples of a 4 level systems as we go along in this particular course, and we are going to see or we are going to just talk about in the thing is a ruby laser. Okay, so yeah, let's talk about the ruby laser then. So first let me draw this thing. Two O three comma C3 that's a chromium and partially reflective mirror this is. Okay, 694.3 nanometer. So emission, as I said, it's an emission. Okay, so yeah, this is a ground level system. 694.3 nanometer. Okay, so the lasing medium, and this lacing medium has a kind of a ruby rod, which as we all know that it's made up of aluminum oxide along with a chromium doped with. Okay, so present in the aluminum gives you the characteristic red color, deep red color, and the crystal, what happens in the inside, what happens within the structure, the electronic resistor structure happening. There is a three different levels: ground state. Okay, so many levels also. So the we might be interested in the transition that has been happening or the transition that is giving rise to the lasing or emission at any point of a time. Okay, ultimately it can release a nanometer, 694.3 nanometer, and we can see the things are rising from one state to another state. Okay, so we have to populate this level, and we want to just make sure that the in flow rate needs to be larger than the outflow rate also, and in order to overcome the loss functions by the stimulated emissions, and uh, we need to just have a longer fluorescence time reserved from the far state, as well as that need to be guaranteed with the ruby crystals, and the lifetime of this chromium ions that can be stayed in a state for a particular order of a milliseconds only. It is a long, really it is a long lifetime, allowing you to be able to really construct this laser. Okay, so actually this we need to take a consideration about the ruby dot, and then the light source that actually take the molecule that the chromium is ion from the ground state all the way to the electronic excited state, and the flash tube typically as they are known as okay, and excited state, chromium mirrors ions then relax back to the state 1 or the lower electronic state, and then due to the fluorescence, due to the spontaneous emissions, if there is a fluorescence that get emitted, and then one of the floors, okay, we put this ruby rod inside the cavity defined by the two mirrors. So just like this. So we need to give some sort of an energy for the discharge resistor tube to flow, and this will push the electronic state configuration of the ions to move from one state to the higher energy level, and when they come they will eliminate it. That's it. But you need to have a large amount of an energy to incident. So it is practical, okay, not much use in the present day scenario, this whole systems, given the advent of the semiconductor lasers and so on and so forth, because it is very inefficient. It takes in a lot of energies of threshold to actually generate the light out, okay, in order to get it out. It has some interesting reserve properties from the fundamental laser point of view, and we will revisit the lasers, and not specifically the design but the laser itself, the ruby laser light emission itself in a different other context. So we will be talking about the coherence also and the spectral data behavior. And another one laser that we are going to do is helium neon laser, okay, how we are going to research it with the many states. So yeah, so in the helium neon laser we have a tubes of some parts. Okay, cathode ring, DC output coupler, AC high volt. This is anode, we are going to change it, okay, helium neon laser, okay, and people used to call this as a high or high reflector, okay, and yeah, let me draw about the electronic state of this one. Normally, okay, 4 level system. Helium neon collision will take place. That is a 5. This is the electronic configurations of it. So how the things will be working. So yeah, let's talk about this point, how the things will be working in this scenarios. Okay, so the laser itself is generated through the mechanism that we know pretty much like that of a discharge tube, except inside the discharge tubes you will have a special kind of an anode and cathode ring. So contains a special mirror, highly reflecting mirror, so they are kept at a brewster angle, okay, and the light is a path will be different, will be slanted to become it is kind of is illuminated at a particular angle, okay. So output resistor couplers will be there, okay, cathode resistor ring, and which will be shaped just like the donut, the electrode that is kept, and we know the anode also is there. And for confining the gas, the helium neon is a gas that have been ionized, okay, helium is a neon gas to a spatial location or a particular point, and you need to have a lot of helium as well as neon gas that has been present here. And what is happening it is when you energize the cathode and the anode, you connect it to a DC high power, high voltage resistor supply. What you need to do is that you end up generating the discharge and ionizing the discharge lamp or the discharge arc and ionizing the gases present also. In response to that, quite a few interesting things started to happen, giving rise to our laser systems. And we can actually write down the laser systems or the electronic structure or the correspond to that in the following manner also. So that is the basically through the discharge, and what we would like to do is excite the helium ions that are the helium, and we need to ionize it. As a result, we need to generate an excited state of the helium and the neon. So we have a helium atom electronic configuration that is in the left hand side also here that you are seeing now. And the helium is as an atomic number of 2, and how there is a collision between these two levels that ultimately result in the generation of a much more uh, uh, particle moment, okay, or electron that get jumped from one state to the higher energy level. Okay, so if you go to this diagram and see the DC high volt cathode ring, anode high reflector, DC output to the coupler. Okay, so because of this kind of a discharge tubes, there will be a kind of a collision between the helium and the neon, which will be just having a more efficient impact on the generation of the life. Ultimately the helium, okay, the excited state atom, helium atom, then collide with your neon. When it gets to collide with the neon, the energy of the neon corresponds to the 5s level, is corresponded to the 5s level. It is almost similar to that of it. As a result, you will get the laser that will be illuminated at a 632.8 nanometer. The energy gap mainly corresponds to that part only. So this caused the helium atom, and because of this discharge, we have discharged the charged particle, the electron with a very high kinetic energy and so forth. They actually effectively excite the helium ions as well as the atoms. Okay, so the helium atoms go into that excited state, which then collide with the neon to transfer its energy to the neon, resulting in the beautiful laser system, which is equivalent to the 4-level systems also. And before it coming back into the ground state. So bandwidth, we know about that. So 0.01 to 0.001 nanometers. Okay. Uh, so such a high receive bandwidth. Okay. With a high receive frequency. Okay. Such a low receive bandwidth with a high frequency, that is 0.1 and 10 power minus 3, it is a nanometer range. Okay, so make the laser light very special. The photon density gives the power of the power. Okay, so power to the laser light. Okay, about the laser light, if we actually look at it, we are investing a lot of energies in generating the light itself. So and from this we can able to get the lasing laser medium, that is a population investor that can be easily researched. It is kind of a unique. Okay, and some of the characteristics that makes a laser emission very useful, that would be one of the foremost thing that comes to us in our mind, is that the coherence, how they are straight without spreading. So we are going to talk about the coherence as well as the spectral brightness right now. So these are the two important things. Let me give you a glimpse about it. So helium, neon, lasing medium, population inversion, high reserve voltage, discharge tubes, collisions. So you will be able to generate the lasers. So right now we are going to discuss about the coherence as well as the spectral brightness. What exactly these are about. Let me draw these things. This is wavefront. And if you have a slit, so there will be these things will be happening. Okay, so yeah, overlaps and it will get bigger and over a period of a time. Okay, so there are different denotions also there and we will be learning about that. Photons are represented with probability of locating the particle. So let's talk about what exactly these two phenomena are and how we are going to name it accordingly. Okay. So every property. So the two most important properties, the coherence and the spectral error brightness, is basically a derivative of one of these characters in our mind. Okay. So for example, monochromicity, or we can say the power. When typically we say it is very intense and stuff like that, they are consequence of one of these properties. Spectral brightness, coherence, the strength, the intensities, how linear they are, the wavefront. Often it might be slightly misleading, slightly loosely spoken up. So when you see in terms or in terms of monochromicity or higher in intensity, because a laser light that is coming out from the helium neon in the order of the milliwatts. So the incandescent lamp that we have in our home, the light that we generate from the incandescent lamp or the tube light or any other light, we mean like a floodlight, it can be of extremely high intensity. They will be spreading it as wide was ran into about watts of the hundreds of watts of light, that energy consumption and the light the generation that we can think about it. It's not just the intensity there is a per se, you can't say just like that, but it is a special other kind of intensity that make it really kind of unique. And then in order to define the more precisely, we are going to take a look at what exactly these two different properties of coherence and spectral brightness have to deal with it. So it can be defined coherence the following is a manner. Let us take an extended source of a light. What we needed, like a source of light like a filament, or for the matter something in terms of light or intensity that comes out from the tube. So it's something that is as a definite length also. Let's call that as length L or extent. So now what we are going to do is finite source can be thought of having there is a many source points. Each of them is what do we mean is by a source point, a single point. So we are going to represent each of them with a slightly different color. Though technically what you are actually is talking about is the same color. Okay, the coherence. So everything is being the same. Okay, so we are going to set a three different color over here in the diagrammatic. I have shown only the one color, and that are essentially the point sources where the laser light can come out over a period of a time. They will get overlap and that will be getting spread out. Okay, so the light emanated from all of this kind of a source point. All are these source points. Okay, so yeah, so we can actually represent the propagations or that light that travels in the following manner as a different emergence of a concentric circles with a particular radii. So these are the places. So if we talk in terms of a light source, now these lines represent a particular the properties also. The property here we are going to talk about is called the wave front. Okay, so here that is a wave front. So the distance increases from the sources as we have some finite property of locating a photons. So what exactly the concentric circles, the radius, the distance increases from the sources, we will get something out of it. Okay, so yeah, the probability of locating a photon that is originally originated from the point which is completely green in color, okay, which we are represented in 1. So we have seen the light source which is a symmetric right emissions. If you are talking in terms of when there is no anisotropic res emission and it is tend to be spherically res symmetrical, so 4 pi solid angle directions, the wave fronts originating from the red point can be thought of representing as a following, and similarity the blue point. So here it's been represented as a single color, but we can do in a different color and see what exactly the curvature or radius has been changing over a period. Okay, so yeah, so what we can say is we can represent all of them as a folk states. We are basically number states. They represent that are related to the number of entities present, the photons. Okay, now this tell us that a state of the NK shells are that or this represents a number or space, a number of entities that we have a state which represents to likely say 0 or 1 or NK also. We have also talked about this and so on and so forth. We have also in a parallel talked about energy eigenstate or in general some other states, right? And we can just think of that as a psi in being this is something called as a state vector describing the quantum mechanical system that we are trying to investigate about that. Okay, probably represents about the probability amplitude, and we can think of the probability amplitude varying in space and time also. Okay, to give a particular given space at any given lesser time, think about the relationship between these two states is that where we are actually talking about the number states also, and functional is a form of a different nature, and that is mainly dictated by the potential and kinetic energy distribution of the particular phenomenon. Okay, so the probability itself of locating the systems, and we try to this figure out where the entities are that are present. In turns, there are typical wave description, they corresponds to our wave description of the light, electromagnetic light radiation itself, or in other words in shorts. Okay, so we need to understand the different set of properties that's been lying around. Okay, and the intensity, the number density of the proton really became the large, where we try to write the description of the systems in terms of the wave functions or the wave themselves. So that's why we normally used to represent all of them in the Fock state, and the eigen energy state and the state there is a vectors also, and the probability of locating the particle in a space. So yeah, the intensity at a particular point P, or the probability of you locate the photon at a point P, is proportional to the linear sum of all the probabilities. So that is the amplitude function of all the waves that originates from S1, S2 and S3. So you take a thing, make a open pores, you pass the lights, ultimately all of this lights will get a converse, the radius will get increases also, the wave fronts will be there, and then this will comes or gives us a different set of a phenomenon with relatable to the Fock states, the probability of finding the particle in a particular phenomenon. So yeah, so in this part, the next part that we are going to discuss the same thing. So what exactly will lead to us, what exactly will give us a detailed understanding about the conditions. So what we are actually looking for is that the probability of finding the particle at a particular locations. Okay, so whether we can able to mathematically denote it or not. So let me start it with the things. 40. So the amplitude probability. Shit. நம்ம தோத்து போறோமா? So we'll explain to us about what exactly I'm writing is all about, how we are going to find the probability of a particular thing in a state, okay, with a certain other partial differential equations also. So yeah, so we are basically writing down the intensity corresponding to the source n, and yeah, so we are thinking of the external light source being having so much of a point. So let's think about one point as well as the intensity of a light, okay, that is kind of a function of it as r and t, that is a distance and time. So intensity of a light and the distance and the time, okay. So the distance has been represented as time as t, and theta and there are phi because of the symmetric reasons, okay. So you will have a theta and the phi symmetric reasons conditions, and yeah, so e I this phi, okay. So for phi n is basically measured at the origin, okay, and is kind of a phase term also, okay. What's exactly happening at the interface, and right, mainly to figure it out the amplitude error function. So this is the amplitude error function, the summation of added up phenomenon with respect to the e power I, okay. This intensity is basically the amplitude square only. So modulus square of the amplitude, okay, the nth source, we try to figure it out the amplitude function taking something, okay. So what exactly in a way to estimate the amplitude at a particular point, okay, we have drawn in many in our pictures. We can think of this as a summations at a particular thing of an individual wave amplitudes with the corresponding interfaces. That's why this one, okay. And we are also talking about the phi n at a point P being measured at a time t1 as well as phi at the same time at the t2 also. That is why the tau t2 minus t1 has been coming into the picture. So we are right now we are interested in the special weather condition, that is a temporal one, and that leads to the condition whether it is temporally coherent or not. We are going to measure this phi n, and then we are going to just see what's exactly happening with it. okay, as an extended light source, we mainly achieve it, then we say that the light is completely temporally coherent. Okay, the delta phi, so the delta phi is lesser than or equal to residual to the pi. So the real experimental quantity that we can actually measure is um, really not the particular one. So we are trying to say that is close to zero in order to reach the temporal erasure coherence. So yeah, so this derivative phi by this dou n, okay, in turn could be a function of a time interval also, okay, that we are actually just looking at it. And if we need to just measure the delta phi, right, the phase difference between the one particular point to another one in terms of seconds. So we do that for light emanating from all of the sources, and then we try to ask a question: is it very constant all throughout the conditions or not? So we try to figure out the time interval where we can able to measure the phase differences also. This is one of the most important point. So phase differences, and finally to conclude about the temporal coherence. Okay, so this T2 minus T1 has a role to play upon, and okay, so you might be asking how the tau phenomena will be playing. That has a role to deal with the coherence time. Okay, so what exactly it means? It means that if we try to measure this delta phi, the phase difference two different between two different set points. So if we try to measure this delta, that is a phi, we will be ultimately getting to know about the two different time scales, how we can able to measure or detect the probability of finding the photon at a particular instance. So yeah, as the distance the light travels in the time period is called the coherence length. That's why this coherence length picture is in. So the light travels in a particular point from one end to the other end. So we can also make a certain conclusion with a spatial or spatial coherence also in terms of integration. So the amplitude of the probability, that is dt, you can rename as a naught e power I phi, and then del phi is equal to phi of probability 1 of finding the particle by 2 It's constant. Del phi. And the volume is the coherent solid. Yes. So yeah, so we try to integrate the amplitude and we try to get rid of the t as we try to seal these conditions. Okay, so we have integrated it over and now we are trying to measure the phase phi across the two different points. Again we are going to measure it, okay, in order to eliminate the one, in order to get what exactly the two giant points. So these are the points in the space and they are continuous in nature also. We try to see the phase difference of the integrated intensities between the two set conditions, and it's kind of a more spatially coherent, and the light source is also spatially coherent. So yeah, and the relationship between the spatial as well as the temporal relationship among these lights coming with us out from the conditions that we try to explain it about, and coherence term for coherence within this extended light source itself, that itself will came into the conclusion. And so the temporal and the spatial as well as the beam eraser profile can be easily spotted with the help of an interferometry concepts, and we are going to talk about interferometry. So and the incandescent light or the flash lamp, the coherence properties are completely different, but this is not the case with respect to the laser set. The laser has a larger coherence length as well as the coherence volumes and has an exceptions also. And yeah, the light from the laser emission is different with respect to the light emission that has been coming from the incandescent bulb with respect to the spectral brightness also. So the power and the watt also we need to take into the consideration to make a certain sort of a things that comes into the pictures. So yeah, so the power in the spectrum region that very concentrated in the spectrum region is completely huge. When you try to focus all the lasers in a particular nanometer, you need to give a large amount of energy to make the things excite also. And the white light source that we took in this example or xenon arc lamp, and we try to generate the laser light continuously in time, but they generate the laser light for a brief period of time, and the brief period of time only. And in order to understand the beam mirror profile, we are going to talk about interferometry. Coherence length and coherence volume will also be increasing over a long period of time. So in the next class we will see all about this thing with respect to the laser output intensity as a function of a time, whether they are steady or continuous or not. So we will be talking this about the pulse laser. What are the conditions that will be existing in terms of the pulse laser? So yeah, in next class we will be talking about all of these things. So I have posted out the assignments over there in the Google Drive. You take a look into it, and we will talk. We will try to just sort out the problem with respect to other conditions also. So yeah, so we will wind up the session for now, and we will see in the next class then. Thank you all. Thanks for attending the session.